This video will talk about voltmeters and ammeters, how they're constructed and how to use them in circuits. This will not cover digital ammeters and voltmeters, but just the basic principles of voltmeters and ammeters. When we use a voltmeter, we're trying to determine potential difference between two locations. So we have a potential difference of voltage across resistor 1, resistor 2, and the terminal voltage on the battery. I should clarify a little bit here on this battery symbol. The EMF is represented these two red lines, and the internal resistance represented with this resistor. This is perhaps a little misleading. You may think that there's one portion of the battery inside its case that produces voltage and a different location back end that has resistance, where in actuality the material that creates the EMF inherently has resistance. So it's not possible to isolate out this internal resistance. It's all mixed in. It's part of the mechanism that makes the potential difference. But when we want to measure potential difference with a voltmeter, we put the voltmeter in parallel. It's very important. We put the voltmeter in parallel. The reason this is done is that the voltmeter tends to have a very high resistance. Modern voltmeters, over 1,000,000 ohms is standard. So if we would put the voltmeter in series, and these are 10 ohms, 20 ohms, 30 ohms, if we put this 1,000,000 ohms in series, that would greatly distort the circuit. We want to make a measurement of the characteristics of the circuit, the voltage and the current, without distorting the operation of the circuit. So if we have 20 ohms, let's say here for R1, and we have 1,000,000 ohms for the voltmeter resistance, you could do the calculation with that reciprocal formula. 1 over Rp equals 1 over R1 plus 1 over R2. You would find that the parallel equivalent resistance is very near to 20 ohms. Putting 1,000,000 ohms here, not very many electrons are going to go through the voltmeter branch of the circuit. The circuit works basically as it did before. So that's how we use a voltmeter, put it in parallel with the circuit. Here we have a situation where we're trying to measure the current in the circuit. So we have an ammeter. Ammeters are placed in series in the circuit. Ammeters have a very low resistance. It's not zero, but it's small, and this will not disturb the circuit very much as long as these are not very small resistors, R1 and R2. So we put ammeters in series. What would be wrong with putting an ammeter in parallel across R1? Say this is 20 ohms, and let's suppose the ammeter is less than 1 ohm for its resistance. 20 ohms and 1 ohm in parallel. That is going to greatly change the behavior of this circuit element. The resistance here, effective resistance, will be a little less than 1 ohm, and we no longer have 20 ohms here, we have a little less than 1 ohm. And there may be enough current to burn out this ammeter if it is carrying all the current that exists in the circuit. Depends on what the values of the EMF and the resistances are. But you put an ammeter in series. Never put an ammeter in parallel in a circuit. Ammeters go in series, never in parallel. The way to construct a voltmeter is to take a galvanometer, a device that measures current, responds to current. It has an internal resistance as part of the galvanometer, and then we place a high value resistance in series. That will create a voltmeter. And of course, it has to be calibrated. We're not going to worry about that. How to create an ammeter? Well, if we have our galvanometer here and we want to measure current, we put in a resistor here that's able to withstand high current, and it is going to be a small value for its R. Most of the current will go through this resistor. Just enough current goes through this branch to operate the galvanometer. And again, it has to be calibrated. But this parallel arrangement, we're going to have a low resistance value. This capital R here will be a small number called the shunt resistance, and it shunts the current, carries the current around, not through the sensitive galvanometer. Just a little bit of current goes through here, enough to operate the galvanometer. And then again, how do we expect to make measurements and not disturb the circuit? Well, if our voltmeter here, very high resistance, our R here, some smaller, much smaller resistance, and the equivalent resistance is still about R, so that's fine. If we get a situation where we're trying to measure the resistance of millions of ohms with a voltmeter that's millions of ohms, then we're going to disturb the circuit. The resistance, the net resistance over here, if these two are equal R's, if you can go through the formula and calculate the parallel resistance, it's going to be R over 2. So we have to avoid this situation. You have to find some other way to measure the potential drop across here other than this voltmeter that has 1,000,000 ohms of resistance. Find some other way. So we avoid situations of measuring voltage across very large resistances. It's okay to put a voltmeter in parallel with a small resistance. That's not going to disturb the circuit much. But if we put a voltmeter in parallel with a large resistance, that will disturb the circuit. Again, the ammeter, it has small resistance, so in series here is fine as long as our R is reasonably large. If the R gets to be about the same size as the resistance of the ammeter, then we have a problem. The ammeter is going to distort the circuit because the ammeter is bringing in a resistance about equal to this resistance in the circuit, and we doubled the resistance here. Over in this left circuit, we've got a large value of R, a small value of R for the ammeter. When we add those two together, we approximately get the R, and it's okay. We can measure the current in a circuit with an ammeter if this resistance is reasonably large. We cannot do this measurement and not disturb the circuit if R is a small number, if this capital R is a small number. So we put voltmeters in parallel. We do this for the case where that parallel resistance is a small number. We put ammeters in series, and we want the series resistance that we're hooked up with to be a reasonably large number. Here we have a voltmeter in circuit here with this battery, this EMF. The current is going to be small because this voltmeter value is high, and we'll be measuring a terminal voltage here that's pretty close to the EMF of the battery. The large resistance here, I, is going to be a small number. There'll be a small voltage drop across the small internal resistance of the battery. So we have the galvanometer, this big resistance inside the voltmeter. That's what's in the circuit element. Situation here of measuring a potential here, taking advantage of a second cell, an EMF here. So this voltage source is going to create a current through this resistance here. This resistance is a special type of circuit element called a potentiometer, and it has a third contact. So we have the two contacts at the ends of the resistance, a third contact here, and the idea is to run this contact to the place that results in zero current through this galvanometer. What we're trying to do is balance the potential of the battery that's here. We create a potential difference across this R sub x that is equal to the EMF of the battery. When we match that, then we'll have zero current in this branch of the circuit. This is a null measurement situation, a null measurement, and it's a standard technique in order to produce accurate values. We make a null measurement, and we can calculate the EMF. The EMF is equal to this voltage drop here. You do need precision resistors. You need a low uncertainty for this value of R sub x. And you need a good stable battery out here that creates a constant current through this resistance branch here. But it is a null type measurement. We're making a determination of the EMF here in a circuit arrangement that has a zero result for the current through this branch of the circuit. So a null measurement. Here we've got an ammeter. We're measuring current that's coming out of this EMF, and we're trying to measure a resistance here. So if we put a voltmeter in across this battery, then we'll get the knowledge of voltage here, the current here, and we'll get a value for R by dividing the voltage we've measured, the potential difference of the circuit, and dividing by the current that the ammeter measures. can you think of some way that this R value might be incorrect? Is there some reason that this R value might be incorrect? We have to be careful here in that we have a situation that this ammeter is putting some extra resistance in the circuit. So we measure the I through here, and it's not just the circuit operating with the resistance here, but we have a situation of measuring the terminal voltage. The terminal voltage is going to vary if this current varies, so we have to have a standard battery here, a nice stable battery, and we can calculate then a reasonably good value for R as long as this voltage remains steady. We do have the potential difference across here. This potential difference is almost the potential difference across the resistor. This potential difference includes the potential difference across the ammeter, though the voltage number is not perfectly correct. But as long as the internal resistance of the ammeter is very small compared to the resistance we're trying to measure, then this voltage number is close enough. Then we'll get a good value for the R. But this voltmeter here, measuring this potential difference, this is not the potential difference across the resistor. This potential difference is the potential difference across the resistor and the ammeter. So V is slightly in error. As long as the resistance of the ammeter is small, very small compared to the resistance here, the value will be a reasonably good value. And then the last circuit we'll talk about here is the Wheatstone Bridge. Again, a null measurement device used to calculate a resistance. We need high quality, accurate values for the resistances in the circuit. And again, we have a variable resistor here. This arrow across the resistance symbol means it's variable. And what is done, we close the switch here, and we've adjusted this R sub 3 until the current reading reads 0. Why would the current in this galvanometer through this branch read 0? Tell me something about the potential difference from B to D if the current is 0. You should be talking to yourself at this point. As long as you don't argue with yourself, you're okay. But talking to yourself and saying, if the potential difference is 0 between B and D, then this current will be 0. And our unknown resistance here is R sub X. So we adjust here. These two branches of the circuit are voltage dividers. There is the same voltage across the full parallel circuit here. So depending on the ratios of the resistances, we get a certain voltage at this point D. The R3 is adjusted such that we get the same ratio of resistances over on this branch. So we can set these ratios equal to each other, and we get a value for R sub X. But again, a null measurement, getting the potential to be the same on both sides. These are voltage divider series resistors, the way they operate. We've got a full voltage across here, V equals IR. There's a certain voltage drop here. There's a certain voltage drop across R3. As we adjust R3 to get the same voltage at point B and point D, this current goes to 0, and we can calculate R sub X. So that's some work with voltmeters and ammeters and null measurements. So with that, we're going to stop, keep reading and asking questions.